Hi everyone, my name is Cassie McMillan and I'm an assistant professor of sociology and criminology at Northeastern University. My research focuses on applying a social network perspective to better disentangle the ways that individuals experience different types of social inequality. In particular, a lot of the work that I do focuses on adolescent populations, and I'm interested in thinking about how patterns of adolescent relationships relate to different types of health disparities, as well as individuals' experiences with crime and delinquency. So across all of this work, I apply various techniques from statistical network modeling, including stochastic actor-oriented models, which I'm going to talk to you all about today. In particular, I'm going to talk about modeling time heterogeneity in these models, which is an advanced technique that will build on some of the basics about SAOMs that you all have covered in previous lectures. So like you all are aware, SAOMs represent a simulation-based method that's really great at analyzing longitudinal network data. The SAOM uses simulations to determine how a social network and individual behaviors of actors within that network, how they evolve and change over multiple waves of data. So using SAOMs, we can answer questions like, are adolescents more likely to adopt the delinquent behaviors of their friends? Are sexual minorities more likely to be the targets of aggressive ties? Is there more reciprocity in our network than we'd expect by random chance? And other related questions like that. So when estimating and interpreting these processes in your standard SAOM, there's one key assumption that we make that's so basic that oftentimes when estimating an SAOM, it's pretty much entirely overlooked. And this assumption is known as the time homogeneity assumption. So this means that the SAOM assumes that the network process that you're interested in, or the behavior change that you're trying to model, it assumes that that change is occurring at constant rates between the panels of data in your sample. So this results in effect coefficients for your SAOM that represent the average level of change across all included waves in your data. So for example, the reciprocity coefficient that tells you whether or not individuals are more likely to send mutual ties in the network, that tells you the average of how these tendencies towards reciprocity, how they work across all of the different waves in your sample. So note that this time homogeneity assumption, not a really big deal if we just have two panels of data. So that means if we have one time period and another time period, just one chunk of time between them, your SAOM estimates are going to perfectly line up with the actual amount of change that's going on between those two waves. However, this assumption gets a little trickier when we're working with SAOMs that include more than two panels of data. So, one of the great things about SAOMs is we can incorporate more than two panels of data when thinking about change over time. A lot of studies that are out there estimate SAOMs on data sets that include 3 to 5 panels of data. So having all of these panels of data is really great. It gives us a lot of information about how networks and behaviors are co-evolving. But again, this calls into question whether this time homogeneity assumption is really correct and really represents our data well. So to better kind of explain what's going on here, let me illustrate this with an example. So here I have some results from a previous study I did where we were looking at data on adolescent friendship and individual smoking behavior. This data comes from the Prosper study that specifically was looking at 5 waves of data from students who attended several schools from their 6th to their 9th grade year. So here me and my collaborators used SAOMs to piece apart whether these processes of selection and influence. So we were interested in figuring out whether adolescents were still influenced by their friends' smoking behaviors after we accounted for all of these other network processes that we also know shape an individual's odds of smoking. So to measure peer influence, we included the average Salter coefficient, which is one of the standard SAOM coefficients that's often used to measure peer influence processes. You can see here, I've circled it in orange. The coefficient is positive and significant. If the average smoking level of adolescents increases by a unit of 1, then you're about 2.5 times more likely to increase your own smoking behavior by a unit of 1, with all else being equal. So that's how we would interpret this positive coefficient here. But again, right, this is giving us evidence that there is a significant tendency for peer influence on smoking in the sample of young people. So when we interpret this coefficient, what we're doing is assuming that this process is the same between all intervals of data in our sample. So we're assuming that as students age from 6th to 7th grade, they're just as likely to be influenced by their friends' smoking behavior as when they age from 7th to 8th grade and from 8th to 9th grade, and so on and so on. So in other words, this coefficient is just the average across all intervals between waves in our sample. So right, this is what's happening, but this raises the question of, right, are there any ramifications to making this assumption about time homogeneity? Well, the answer there, it really depends on what's going on in your actual observed data. So sometimes this assumption is completely fine to make, and it lines up really well with what's actually going on in the data that you're looking at. So right in our sample here, perhaps it was the case that kids were just constantly more likely to increase their smoking as the behaviors of their friends started smoking more and more. So here in this table I have to the right, I have one potential option of what could be happening in the observed data that I've labeled as option 1. And here you can see between each panel of data, so right, wave 1 was collected in the fall of students' 6th grade, wave 2 was collected in the spring of their 6th grade year. So this is our first panel of data. And then second panel, third panel, and fourth panel. So here in option 1, we're seeing that the coefficient for that friend's average smoking parameter is 0.93 at every single period of data that we're looking at. So right here, kids are constantly more likely to increase their smoking as their friend's smoking behavior increases. Other times, however, the average that we get from our time homogeneous coefficients might obscure key variations that arise across the different waves of our data. So this is what's happening here in option 2. Here you can see that between those first 2 waves of data, we have a really large positive coefficient for peer influence. So in early adolescence, kids are really likely to be influenced by their friends' smoking behaviors. But as you can see, as time goes on, the size of this coefficient dissipates. It gets smaller and smaller between each of the subsequent waves in our data. And then between our final 2 waves, we see that the size has lessened all the way to 0. So this indicates that there is no evidence for influence. Instead, right, it doesn't really matter what your friends are doing. It doesn't shape your odds of smoking whatsoever. So from looking at option 1 compared to option 2, we can see that option 2 is telling a very different substantive story than what's happening in option 1. Right, if in our observed data, we're seeing something that looks more like option 2, that has really different implications for how we should design smoking interventions in early adolescence versus middle adolescence. Well, option 1 suggests that an intervention program that targets peer influence will probably operate similarly across these different waves. So because of the assumption of time homogeneity across waves, standard SAOM coefficients aren't able to distinguish between option 1 and option 2. Both are going to produce the same average coefficient that we found in our project. So if you go through these coefficients I have for option 1 and option 2, if you add them up, take the average, you'll see that they both have an average of 0.930. So there's no way to distinguish what's happening here if we just use our standard SAOM coefficients that you all are familiar with. So today I'm going to cover some ways that we first can test whether or not there is Today, I'm going to show some ways that you can first test whether or not this time homogeneity assumption is valid. If it's not valid, or if you have theoretical expectations for why there should be differences in network processes over time, then I'll next show some ways that we can model the evolution of the network and behavioral processes in a way that allows one to really account for the time homogeneity that we're observing. So right, when I showed you those 2 different options of what could actually be happening in our observed data, it was clear that right in option 2, network processes, specifically peer influence, were operating differently at these different periods of adolescence. right? So network processes might be present in between some periods of our study, but not others. But this still raises the question of why is this something that us as networks and health researchers might actually care about? So a couple of reasons why you might want to think about time heterogeneity when estimating SAOMs. The first reason I have here is a bit more substantive, while the second two are a bit more technical. But starting with the substantive reason, sometimes you might have research questions that are interested in time heterogeneous processes. So for instance, a lot of theories about adolescent development suggest that experiences with different peer processes like peer influence or the link between substance use and popularity, a lot of these theories suggest that these processes are probably going to vary over time as folks get older and as they age through adolescence. So right, you might have a research question where you're interested in how these network processes differ as people get older. Also, considering these time heterogeneous network-related processes might be of interest if you had some sort of treatment that occurred in your data, between different panels of your data. So perhaps you had you had data both before and after a smoking prevention took place that taught skills about resisting peer pressures. By considering time heterogeneous measures of peer influence, you could empirically test whether the magnitude of peer influence significantly decreased in your network after everyone experienced the intervention. I'll walk through an empirical example from my own work where I show some techniques for how one could go about this. Moving on to the more technical reasons about why we might care about time heterogeneity. Reason number two, one of the reasons that this is the time heterogeneity is something you might be interested in is because failing to account for different time heterogeneous processes runs the risk of biasing parameters in your model. And this is the case even if your key parameter of interest isn't shaped by time heterogeneous processes. If other time heterogeneity is not well accounted for, then your key independent variable might still take on some undesirable properties like inconsistency or poor efficiency. So it's important to make sure that we are accounting for any time heterogeneous parameters. Final reason that time heterogeneity is worth thinking about is, like I'm sure you all are aware and have learned about so far when working with SAOMs, SAOMs face a lot of problems with degeneracy and convergence. So it's really, really crucial to make sure you can correctly specify these models if you want to get good quality, well-converged estimates. As a result, correctly specifying time heterogeneous parameters can really improve the fit of your model and how well it actually fits onto your observed data. So in other words, by correctly modeling time heterogeneous processes, you can reduce your risk of experiencing degeneracy in your SAOMs. So to conclude, pretty much anytime you're working with more than 3 panels of data, it's really worthwhile to consider whether or not time heterogeneity is shaping your network and behavioral processes. So before we dive in about how to incorporate time heterogeneity into our SAOMs, I first want to give a quick review of standard time homogeneous SAOM functions. I'm going to do this by talking a little bit about what's going under the hood by focusing on some of the formulas that are guiding the SAOM. But I'm not going to get too into the weeds here. Instead, if you're really interested in kind of the math that's going on for these time heterogeneous processes, I point you towards this article that Waspinoso wrote with his colleagues in 2011. And I have a site for that at the end of the presentation if folks want to read more about this. But anyways, recall that SAOMs include a rate function as well as an evaluation function. The rate function has to do with determining how often each actor gets the choice to make a change, while the evaluation function is dictating how they are actually going to decide what to change. So both a rate and an evaluation function are used to model the changes in the network as well as the changes to individual behaviors. In the example equations that I'm going to show today, we're just going to be looking at changes in the network, but the same logic applies when you're thinking about changes to behaviors. So the SAOM right? It's a series of mini steps where an actor evaluates their position in the current network and compares that current position to all possible states of the network that could exist if they made one single change to their ties. So this is essentially what the left-hand side of the formula is telling us. An actor will only dissolve a tie or form a new tie if they deem that the network change that would result from that tie difference would result in a network that's more favorable to their current position. So how do they decide what's more favorable to what they're currently experiencing? This is where the right-hand side of the formula comes into play. So here, S sub I is a vector that contains all of the structural features of the network as seen from the point of view of our focal actor or actor I. Then this beta here represents a transposed vector that includes all of the statistical parameters of interest that are specified by the user who's estimating the SAOM. Finally, this xi send to j models actor I's choice to send or dissolve a tie to all of the other actors in the network. So after you calculate this Fij of x, then it'll be used to estimate the conditional choice probabilities that actor I decides to change a tie in their network. And it's those probabilities that are used to calculate your SAOM coefficients, which we can then interpret and make substantive conclusions from. All right, so if we want to introduce time heterogeneity into our effects, what's going on under the hood looks really similar, but there are a couple tweaks that we need to make. So first, we're going to be looking at specific periods of time between panels, as denoted by A. This is the period of time between two adjacent waves, so between wave 1 and wave 2, or between wave 2 and wave 3, so on and so on. The right-hand side of this equation now equals a possible state of the network during period A. So this is a possible state of what things could look like, but just during that one period A. Next, you'll see, if we turn to the right-hand side of the network, we'll see how it is calculated. You'll see now we have a sigma. All this does is allows us to go through all of the different effects in our SAOM and pull out those effects specifically labeled as K. So those K effects that we want to model as being time heterogeneous across the waves of our study. So what comes next looks a little different, but the same idea as what we had before. So here beta is a statistical parameter of interest for effect K. So beta here is just going to be a single value as opposed to a vector, since sigma is letting us go through our effects one at a time. We're also now introducing this lowercase delta, which is this symbol here. And here, all this is an interacted time dummy with effect K, so our SAOM effective interest, and for specifically time period A. So by including this, we can test whether the statistic for effect K is significantly different during period A than it is from the baseline. So these time dummies allow us to capture the magnitude of an effect during a specific period of our data. Instead of taking the average of the effect across all the different waves, now we can consider each period on its own. Okay, so now that we know a bit more about what time heterogeneous effects look like under the hood, let's shift gears and talk more about how we actually introduce these time heterogeneous effects in our plan of analysis and how we make sense of what our results look like. So even if changes in network processes over time aren't of interest for you in your research question, there's still a lot of value in testing for time heterogeneity across the parameters in your model, as this can improve model fit and increase the robustness of your findings. So Laspinoso and his colleagues developed some techniques to do this in Siena. They basically build off conventional statistical tests that you're familiar with, things like Wald tests, that will consider whether a network effect, like peer influence, varies between the different waves of your study. For these tests, your null hypothesis is going to be that your deltas, or the interacted time dummy coefficients, your null hypothesis is that these equal 0. This means that the process that you're interested in remains constant over time. So in the lab that I'll walk through with you guys, we'll see some examples of this and discuss how this shapes your interpretation of your findings and what to do as you move forward. So if these statistical tests uncover a significant difference across time, then the next thing we need to do is incorporate time heterogeneous effects into our SAOM. The way we do this ends up being quite simple, especially from the coding side and what we see in R, but also for the interpretation as well. Essentially, what we will need to do here is include a set of dummy variables that represent each time period between the waves of the study. So again, here the time variables don't represent individual waves, but instead what they're doing is representing the periods of time between waves. So we'll have a time dummy for the period of time between wave 1 and wave 2, between wave 2 and wave 3, and so on and so on. So a dummy for one of the periods will be excluded, and this will serve as your reference period. Typically, what you do is select the first period as your reference. The dummies themselves aren't particularly interesting to us. There isn't really much substantive meaning we can get out from them. Instead, what Sienna does is it sets the coefficients for these time dummies to 0, and we typically don't interpret them substantively. Then what we do is we include interactions between the time period dummy variables and each network effect of interest. So this network effect can be something like peer influence for smoking, reciprocity, popularity for smokers, so on and so on. By including these interactions in our models, by interacting this effect of interest and the time dummy variables, then we're able to consider whether the strength and the direction of different network processes varies across the periods of our study. So the coefficient for each of these interactions will tell us whether or not there is a significant difference between the reference period, or that first period that we're looking at, and that later period of interest. I'll walk through some more examples of this. We'll also see examples of the lab during the R lab, and this should help kind of solidify what I mean here by these different interactions. All right, so next I'm going to show an example of how I've incorporated time heterogeneous effects into some of my ongoing research that I've been doing with Brittany Freeland and Mark Feinberg. In this project, we are interested in thinking about how the normative transition from elementary to middle school shapes adolescents' experiences with delinquency-related processes. So first, I'll give a little bit of background to explain our thought process here. As you can probably guess, adolescence is the time period when involvement in delinquency peaks for most individuals. However, individual offending trajectories aren't identical for all youth. So to explain these differences, life course scholars have pointed to turning points or transformative life transitions that individuals experience during the course of their life. So turning points can help understand the variation, or help us understand the variation that defines young people's offending patterns, and they can help us kind of figure out why some individuals desist from criminal activities while others remain involved for their entire lifespan. So some of the key turning points of interest that occur during adolescence include things like dropping out of school, experiencing a parental divorce, as well as experiencing just normative changes from lower level schools to higher level schools. So for instance, just the standard change from elementary to middle school also has been labeled as a turning point as well. So previous work finds that these crucial life changes can either increase or decrease one's involvement in delinquency. So for example, this transition from lower level schools to higher level schools has been shown to significantly decrease one's odds of participating in delinquent activity. So this graph that's presented on the left, you can see that, right, for young people who attend school in a transition district, after a transition occurs, their delinquency kind of levels off, while folks who go to school in districts where there is not this transition, they don't experience the same kind of shock to their own individual delinquent behaviors. All right, so that's some background about how life course scholars have been thinking about these transitions. But bring a bit more of a network perspective to this problem, we also know that adolescents' decisions about whether or not to participate in delinquency don't occur in a social vacuum. Instead, right, we know that kids are influenced by their friends' delinquent behaviors. In some contexts, delinquency is associated with higher levels of popularity. In other contexts, it's associated with lower levels of popularity. But despite the fact that we know that peers are really important for individuals' delinquent behaviors, we don't know very much about how turning points shape network processes related to antisocial, risky delinquent behaviors. So, in other words, after turning points, do adolescents who are delinquent become less popular? Do they become less social? Or do the networks become more clustered according to individuals' delinquency participation? If delinquent youth become more marginalized in their networks, such that they're kind of pushed to the peripheries because of these changing social processes, then it'll be harder for delinquent influences to spread to these pro-social peers. So, right, if delinquents are all on the periphery, it'll be harder for pro-social youth who are in the core of the network to be exposed to their negative influences. So in the example that I'm going to walk through with you all today, I'm going to focus specifically on delinquent popularity. And here, what we're going to do is see if the association between delinquent popularity and receiving ties, does that change both before and after the transition? So to understand the output, let me first say a couple of things about the data that we use to address this question. So we're using data here from the Prosper Peers study, which is a large longitudinal study that followed adolescents in semi-rural and rural communities in Pennsylvania and Iowa. We're focusing on 5 waves from the study in this grant project that were collected each spring in students' 6th through 10th grade years. At every wave, sociocentric friendship network data was collected by asking the students to nominate their closest within school and within grade friends. Because we're looking at 5 different waves, that means we're looking at 4 periods between waves. So time heterogeneous effects will allow us to determine whether delinquent popularity processes are similar or different between these periods of time. Also note that our sample includes over 50 different school cohorts. So we have a little over 50 different longitudinal networks from different school districts. Some of these school districts transition kids from elementary to middle school between 6th and 7th grade, which is our key transition of interest here. But other school districts have alternative transition structures. So for instance, a lot of the schools are K through 8 schools where you have kindergartners through 8th grade all together in the same building. So as a result, this allows us to kind of conduct a sort of pseudo experiment where we can test whether or not these school changes have meaningful impacts on delinquent popularity compared to a control group that didn't experience the same transformative change. So we do this by estimating SAOMs on each of the schools separately, and then using a meta-analysis technique to combine our results for different types of networks according to their transition structure. Finally, delinquency is operationalized as a 12-point variety score. So kids were asked whether or not they participated in 12 different delinquent acts over the past year. The variety score counts up how many acts they admit to participating in. The different types of delinquency that kids were asked about range from things like getting into fights, to vandalizing, to stealing items, and skipping school. All right, so to account for delinquent popularity, we're using the altered network effect. This is just a standard SAOM effect that's used to test whether or not actors who have certain individual traits are more or less likely to receive incoming ties. So again, like I mentioned, we're using a meta-analysis technique to combine the results for the different networks. If you're interested in learning more about the meta-analysis that we did, I highly recommend Dan Reagan's presentation on this topic that he did for last year's Social Networks and Health workshop. That's still available online if folks are interested. But kind of in sum, the way that we'll interpret the coefficients for these meta-analysis is essentially the same way that we would do so for a single SAOM. Again, here we're compiling the SAOM coefficients for the transition and the non-transition schools separately. Because we want to compare what's happening in the transition schools to what would be expected to happen in absence of the structural change. So first here, I'm presenting the results from the time homogeneous versions of the delinquency alter coefficient. Again, right, this is just the standard SA1 coefficient that you're used to seeing. Starting with the non-transition districts, here we can see that the delinquency alter coefficient is positive and significant. This means that in non-transition districts, delinquent youth are expected to receive significantly more friendship ties than their non-delinquent peers. If we move over to the transition district models, here we see that the coefficient is positive, but it is much smaller, less than half the size. It also is no longer statistically significant. So we have no evidence that in those transition districts that there's any association between delinquency participation and receiving friendship nominations. So can we conclude that the transition to middle school reduces delinquent popularity from looking at just these time homogeneous coefficients? No, we can't, because right here, we don't know whether or not these differences occurred before or after the transition took place. Well, we have waves of time that occurred before the transition and after the transition in our data. What these time homogeneous delinquency alter coefficients are doing is they're averaging all this change together. So we can't, from just looking at these coefficients, answer our research question. We don't know whether or not the transition significantly changed delinquents' experiences with receiving friendship nominations. So this is where the time heterogeneous effects really come into play. So here I'm showing a new set of SAOMs that we estimated, the results from these. And here the new SAOMs are incorporating a time heterogeneous version of the delinquency alter coefficient. So first I'm going to walk through what these new parameters are, and then we'll go through and interpret them. So remember though that we have 5 waves of data. That means there's 4 periods of time between the panels. So we'll consider how this delinquency alter coefficient varies across these different panels. So the first thing that we do in the time heterogeneous model is we calculate, or we include these different time period dummies. So here for every single period in our data, we have a dummy variable that you can see here. We omitted the first period. So the first period occurred between 6th and 7th grade. That is serving as our reference category. But then we have dummies for each of the others. Note that we typically don't interpret these dummy variables at all. Instead, what goes on is Sienna automatically sets their coefficient value to be a 0. So not really of substantive interest for us here. So even though we don't interpret the time period dummies, they're important to include because we use them to create interactions between the dummy variables and our key network effect of interest. So here you can see at the bottom of the panel, what we're doing is we're interacting the time dummies with the delinquency alter coefficient. So by including these interactions, the coefficient for this original delinquency alter coefficient comes to represent what's happening during the first period of our data. So what's happening between that first wave and our second wave. So here it represents the strength and direction of delinquency alter during those first two, or between those first 2 panels of data, which were between 6th and 7th grade or before the transition occurred. The coefficients for each of the interaction terms, what's located down here, then indicate the difference between the first period and each subsequent period of time, all of which happened after the transition occurred. So here, significant interaction coefficients suggest that there is a statistically significant difference in the tendency for delinquent youth to receive friendship nominations in this process after the transition occurs. All right, so what do the results actually tell us? We'll start with the non-transition districts. So here the baseline delinquency coefficient is positive and significant. So this means that between 6th and 7th grade, there is a significant tendency for delinquent youth to receive more friendship nominations. If we move down to look at these interactions though, we see that none of these interacted time dummies are significant. Right, they're all very small numbers and none of them reach statistical significance. What this means is that every subsequent period in the non-transition districts looks just like it did for the first period. So across the entirety of the waves in the non-transition districts, delinquent youth are continuously more popular across the whole study. All right, so how does this compare to what's happening in the transition districts? If we look at our other models here on the left, we can see that before the transition occurs during the first period, we again have a positive and significant delinquency alter effect. It's about the same size even as what we saw in the non-transition districts. So this means that before the transition occurred, we have a significant tendency for delinquent youth to receive more friendship ties than their non-delinquent peers in the transition schools. However, now the interactions are suggesting different patterns. Here, now we see that all of the interactions are negative and they are statistically significant. So this means that all periods of time after the transition occurs, we should see delinquent youth receiving significantly fewer nominations than they did before the transition took place. Since these are kind of abstract concepts, I think it's often really useful to plot out your findings using a bar chart. Here I've done an example of what I had in that previous table, where here the y-axis is telling us the expected coefficient size of the delinquency alter coefficient. We're doing this across all periods and for both school types. So here the yellow bar represents the non-transition schools and orange represents the transition schools. So by walking through this, we can see that before the transition occurs, so in period 1, the delinquency alter coefficient is about the same in both of these two districts. And from doing more rigorous tests, we found that there is not a significant difference in these coefficient sizes. However, after the transition occurs, you can see that things change up quite a bit. So in the transition districts represented by the orange bars, we see that now the delinquency alter coefficient is negative, indicating that delinquent youth send or receive fewer friendship nominations than their non-delinquent peers. The yellow bars, though, representing those non-transition districts, indicate that in schools where this transition didn't take place, we're actually seeing delinquent youth continuing to receive more nominations than their non-delinquent peers. So in sum, what this is showing is that after that normative school changes, like the change from elementary to middle school, can decrease delinquent popularity. So in absence of this normative change, delinquent popularity isn't expected to change. However, there are significant changes to this network process after a school transition occurs. We argue that because delinquents become less popular, they're pushed to the peripheries of the networks that they are a part of. As a result, there's fewer opportunities for pro-social youth to be influenced by these by the behaviors of these delinquent peers. So taken together, we think that part of the reason why delinquency tends to decrease after school transitions occur really have to do with these changes in peer processes that we are finding in our data. So as we walk through the RLab, I'm going to show some more examples of how to interpret and present results for time heterogeneous coefficients. So you'll get some more experience at making sense of these different types of SAOM coefficients. Before I do that, though, I do want to point out a couple of helpful resources for using time heterogeneous coefficients in SAOMs. As I mentioned before, this piece by Lospinoso and colleagues really walks through a lot of the different math and statistics behind everything that's going on with these coefficients. There's also two empirical examples of studies that have applied these coefficients and substantively interpreted them that I've pointed out here. Finally, the RCNS tutorial webpage has a R script that walks through how to incorporate the different Siena functions for estimating time heterogeneous effects. So that's a really useful resource to keep in mind as well. All right, so now that we've covered some of the basics about modeling time heterogeneity in SAOMs, I'm going to walk through an RLab that I've put together, the script here, that will show you how to actually estimate these effects in using our Siena. So the data that we're going to be using today comes from Van de Bunt's study of a couple dozen college students. You can access the data and read more about it at this link here. It's used in a lot of these different SAOM example applications because it's a relatively small and easy to work with data set. So if you go to this website, you can download a zipped file that has all the data that we'll need today. Specifically, there's 5 different pieces of data in there that we're going to be working with. The first 4 are network data sets that are stored as adjacency matrices. And then the final one is a data set that includes several actor level characteristics. So go ahead and get those downloaded and saved to a directory on your computer. Then once you have that done, you can come back and set that directory as your working directory. So I'm going to go ahead and do that now. Then the next thing that we're going to do is load in all of that data into our R environment. So participants were asked in this original data that was collected, the participants were asked to rate their relationships with all of the other students who were in the study according to a 6-point scale. But for the purpose of this lab today, we're going to simplify this so that the adjacency matrices are binary networks where a 1 indicates that there was a friendly relationship between 2 actors. So first, we're going to recode all the friendly relationships as 1. Currently, there's a category for best friends, friends, and friendly relationship, but we're going to collapse those all to be the same thing. And then folks were also asked to report on less friendly relationships. We're going to recode those as 0. So this includes acquaintance relationships as well as troubled relationships, so sort of negative relationship there. Next, there's some missing data as well, and as you all know, one of the cool things about Siena is that it has some built-in features to account for missing data, so we'll go ahead and take advantage of those by coding all of the missing data as an A. All right, so the Van de Bunt study that we're going to be using also collected data on respondent smoking behavior. Currently, the data is coded in a way that's not great for interpretation purposes. So currently 1 indicates that someone is a smoker, while 2 indicates that they're not a smoker. But we're going to recode this so that smokers are 1 and non-smokers are 0, just to help us out with interpreting the results. All right, so now that we've cleaned our data, let's pull everything together and put it in a single data object that we can use when estimating our SAOMs. So the 4 panels of those friendship network data sets that we created are going to operate as our dependent variables. We'll use the Siena dependent function to indicate that. First, though, let me make sure that I have our Siena in my library. Now I should be able to run that code here. Then, like I mentioned before, we have this data on smoking about all the individuals. For the sake of simplicity, though, we're going to just treat this as a constant covariate rather than a time-varying covariate or a different variable. Instead, we're just going to assign 1 for each of the respondents that remains constant across. We also have information that we're going to treat as our constant covariate, so we can construct some additional controls. So now that we have these different data objects, let's pull them all together and create a Siena data object using the Siena data create function. Now we have an object in our environment called full data, which is what we'll use continuously when we estimate our SAOMs, because that stores all of our data. All right, so the first thing that we're going to do is just estimate your standard SAOM that doesn't include any types of time heterogeneous effects. Instead, this will all look really familiar to what you've learned about before when learning about SAOMs and working with Siena. So in order to do this, the first thing we need to do after we create our Siena data object is to specify the effects. In order to do this, we'll use the get effects object and just put in, again, our data that we created with the Siena data create function. So now we have just the standard full effects object, or get effects object. And right here we have all our standard parameters that aren't super interesting substantively, at least, but crucial parameters to include. Next, using the set effects function, we'll add some other effects of interest. So first we'll add two endogenous structural effects. Trans-trip is the transitive triplet effect that accounts for whether or not there are tendencies towards triadic closure or transitivity in our networks. Then the trans-reciprocated triplet effect is this next effect. And what that is doing is it really just kind of reduces the bias of the transitive triplet effect. So that's why we're including that one. Next, we're going to include some actor-based network effects. So the first is an ego effect, specifically for smoking. So this variable is going to test whether or not smokers tend to receive more ties as compared to non-smokers in the network. Next, we have an alter effect for smoking as well. So this does kind of reverse of the smoker effect. The smoker alter effect is testing whether smokers tend to receive more ties than their non-smoking peers. Next, the smoking same parameter will test whether or not there's homophily on smoking. So are smokers more likely to prefer other smokers as friends? Non-smokers tend to prefer other non-smokers. And then we also have gender as well to account. Now we can see what all the effects are that we are including. Now that we have the effects specified, the next thing that we need to do is set the algorithm settings that we'll be using to estimate the SAOM. So we're going to use just the defaults for today's lab, but do keep in mind that for models that are like publication quality wise, you will need to tweak some of what's happening in this Siena algorithm create function. But here in the algorithm create, we're going to give a name to the file where all of our output is going to be stored. That'll be saved to your working directory that you stated at the beginning of lab. We're also using a random number seed, which will just ensure that we're all getting the same results when estimating our SAOMs. All right, so now that we have the algorithm, the data, and the effects all saved in the format that Siena and R like, the next thing that we're going to do is estimate an SAOM to serve as our baseline. Here, all of the effects in the SAOM are time homogeneous effects. So again, this will look very familiar to other SAOM examples that you've seen before. All right, so here we're using the Siena SAO07 function to actually estimate our model. And you'll see after you run that, this little bubble will pop up to say where things are going. You can also turn this off too if you don't want to look at that. All right, so now we have our output saved in this my results one object. So I went ahead and clicked that to see what it looks like here. And here you can see, right, this is the Siena output you've seen before. All of the effect coefficients that are included assume that network processes remain constant across all periods of the study. So for example, if we look at the reciprocity effect here, we can see that it is positive. Standard error is really small, so it's definitely significant as well. And what this means is that across all waves of the study, on average, we're seeing a tendency for individuals to send mutual ties to those who they have received ties from. So, right, we're assuming that this tendency for ties to be reciprocated is remaining constant between all of the different waves in our study. But right, this wave raises the question of, is this a correct assumption to make? Here we're working with 5 different panels of data. So right, lots of different periods of time that we could be looking at. So in order to test whether or not the time homogeneity assumption is correct, what we do is we use the Siena time test function. So this is a new function that is not included in the standard kind of toolkit of SAOM functions. Instead, this function is specifically used to test for time heterogeneity. So the way that you'll use the Siena time test function is first you'll need to estimate an SAOM like we did here. And then you can include the results of your whatever you named your Siena 07 function output. Here we named it my results 1. So that's the only argument you need to include in the Siena time test function. So here we are going to save the output in this object called time test 1. If we just check on the output, you can see that what we get is a whole bunch of information, but it's really only what's on the first couple lines that's of interest to us here. So you can see here what we did was a joint significant test of time heterogeneity. So essentially what we're trying to do is see whether or not there is any evidence for any of the effects being shaped by time heterogeneity in our model. So it does this using a chi-squared test, but the main thing that we need to pay attention to here is this p-value. So specifically, because we're trying to test whether or not there is time heterogeneity in our sample, what we're looking for is a p-value that is greater than 0.05. So it's greater than our significance threshold. Typically 0.05 is used as the significance threshold in the social science literature. So if we have a non-significant p-value, what that indicates is that we don't have any support for our hypothesis that there is time heterogeneity in at least one of our effects. But like you can see here, the p-value is significant, it's 0.0025. So it looks like there is some time heterogeneity going on here. As a result, we can use this summary function to get more information about what's going on in our model. So here you can see the summary function gives a whole bunch more detail. You start again with that joint significance test results, but then what's important to note is you get this individual significance test result as well when you use the summary function to pull out more information from the object. And here you can see what we have is first just all of the parameters we included. So, right, this looks really familiar, just like the parameters we included in the model. It also gives the p-values here, so it tells you whether or not the coefficients were significant. But the next thing we have is we have potential interactions between each of the parameters and the time dummy for the periods of interest in our study. So here, what this is telling us is whether or not there is evidence in our observed data that any of these processes are operating differently in the first time period than in the later time periods. So I think it's easier to kind of understand this with an example. Let's focus on that smoking alter coefficient down here. So right, smoking alter is testing whether or not smoking is associated with popularity or receiving more friendship nominations. Here we can see that dummy 2, so for period 2, between waves 2 and 3. Here, if we go and look at the p-value side, no evidence that there's any real heterogeneity there. But if we look at what's happening in period 3, here we're getting a p-value that's very, very small. Also, this middle column about kind of what's happening between the different steps. Here, we're getting a negative number. So it looks like what's happening is that there's some big changes occurring with the association between smoking and individual popularity. There's some additional information here too that kind of sums things up. But what's also useful to do with this output here is that we can create some plots to help us kind of better visualize what's happening. And we can do this just by using the plot function. Here, we're calling effect 6, which is the smoking alter effect. And we know that from looking at the very bottom of our output for the time test information. So if you scroll to the very bottom, it'll say use the following indices for plotting, and smoking alter is 6. That's why that 6 is there. But anyways, moving to what the plot actually looks like, here we can see kind of like how the parameter value of the smoking alter coefficient, how it's expected to change at the different periods of our study. So you can see here in period 1 and period 2 tends to be pretty similar and pretty large and positive. But after, during the third and final period of our study, things changed quite a bit. So here, smoking alter is changing quite a bit and now even becoming negative. So taken together, all of these tests are indicating that the tendency for smokers to receive more or less nominations than their non-smoking peers isn't consistent across the waves of the study. So what's happening between wave 1 and wave 2 is really different than what's happening between wave 3 and wave 4. So we can further kind of piece apart what's going on here by breaking down that smoking alter effect into multiple interactions between the time dummy variables. So I'm next going to show you all how to do that by incorporating another new Siena function. But first, to make things easier, let's just copy over the same effects object that we were working with before, but we're going to call it full F2 now. Now, using a new function, the include time dummy function, what we're going to do is add the time heterogeneous effects to our models. So a couple arguments that I'll walk through for this function that allow you to do that. So first, we're going to use just include time dummy here instead of the set effects function like you've used before. And when we use the include time dummy effect, the first thing you'll want to include is just an object of all the Siena effects. So here, full effect 2, what we just created up here. The next thing you want to add is information about which specific parameter you want to add time heterogeneous effects for. So here we're looking at the smoking alter parameter. That's why we're calling alt x. Then we're using the interaction argument to specify that we're looking at alt x for smoking because, right, we have multiple actor level variables. So we have to tell Siena which one we're interested in looking at. Then finally, what we're going to do is use the time dummy argument to specify that we are interested in creating dummy variables for all of the time periods, excluding the reference period. So here, just in quotes, you need to write the word all, and then the include time dummy function will know what you're talking about. So we'll go ahead and run that. We'll get some output. But now, let's go ahead and check out our effects object. And here you can see that when we look at our effects, a new column has emerged that we haven't seen before. This column is labeled time dummy. And we can look down here and see that for the smoking alter effect, now it says all in that row. So that just means that for the smoking alter effect, we're going to create interactions with the time dummies for all of the periods except for our reference period, which is the first period of our study. Here where there's commas, that just indicates that there aren't going to be any interactions with the time dummies. Instead, we're treating that as a time homogeneous effect. All right, so now let's estimate the new SAOM with the time heterogeneous version of the smoking alter effect. We're just going to create a new algorithm for that and then use the Siena7 function to run our models. All right, that's about finished up. Then we can check out what our results look like. And here is again where these time dummies and interactions are going to come up, and you'll be able to see what that looks like. So right, again, here's the results. They look really similar to your standard time homogeneous SAOM results. We still have that smoking alter parameter here, but now we have some additional parameters that we haven't seen before. So first, we have these two dummies, which are the time dummies. Here again, right, we don't really interpret these. Siena automatically sets the coefficients equal to 0. Instead, that's just included so that we can create these interactions that you see on line 11 and 12 here. So the first interaction is between the second period and the smoking alter. So that tells us whether or not the second period of time is significantly different from the first period of time for the smoking alter coefficient. While the final parameter here is an interaction between the third panel of time and the smoking alter coefficient. So I next have some code that walks through how we actually interpret what's happening here, and provides kind of the math for how we exponentiate these coefficients and interpret them as odds ratios. So again, like I mentioned in the lecture, the way that we interpret now this new smoking alter coefficient is that it tells us whether or not there is a association between smoking and popularity during the first period of our sample. So during what was happening between wave 1 and wave 2. So we can take that coefficient there, which is 0.32 about, and exponentiate it to get the odds there. So I have some math there for how I calculated that. But in general, what we're doing is, or what we can conclude is that between wave 1 and wave 2, for every 1 unit increase in an individual smoking behavior, they were expected to see a 38.1% increase in their odds of receiving an additional friendship nomination. So in general, or more broadly, smokers tended to receive more friendship nominations during the first period of the study. And we can tell that that's significant too if we look at the standard error there. It's the coefficient's more than twice as large as that standard error. So we have significant evidence for this association between smoking and popularity. If we want to compare what was happening in that first wave to what was happening in the later waves, what we can do here is add together the different coefficients and use that to estimate and explain what was happening. So if we add the coefficient for the smoking alter coefficient to the coefficient for the first interaction, that interaction with the second time period and smoking alter, what that will do is help us illustrate the relationship between smoking and popularity between waves 2 and wave 3, so the second period. So by exponentiating things, we can conclude that between waves 2 and 3, every 1 unit increase in an individual smoking was associated with about an 18% increase in their odds of receiving additional friendship nominations. If we go back to the SAON output, we can see that the standard error for this interaction is quite large, about twice the size of the coefficient. Thus, it is not going to be statistically significant. This means that there is no significant difference in what was happening between wave 1 and wave 2, and between wave 2 and wave 3. So during all of those waves, adolescents who smoked were consistently more likely to receive friendship nominations than adolescents who did not smoke. All right, moving to the final period of the study, or what happened between wave 3 and wave 4. Again, we can add together just the coefficient for the smoking alter, and then the coefficient for the respective interaction. And by doing that, we can get information about what was happening during that final period of time. So we can do that here. And from exponentiating everything, we can conclude that between those final 2 waves, every 1 unit increase in smoking was associated actually with a decrease in receiving additional ties. Again, this interaction is significant, which if we go back to the output here, we can see that, right, the standard error here is quite small. So this indicates that there is a significant difference in the association between popularity and smoking in that final wave of the study. So things sort of reverse as the college students in the study get older. So again, when working with interactions in general, I think it's really helpful to make graphs that show what's happening to better tell one story. So I have some code here for how to do this in this current example that uses functions from ggplot2. If you haven't used ggplot2 before, make sure you first install the package before loading it up in your library. And then just by walking through this, we can get some bar graphs. Here, what this is showing is the y-axis is telling us the size of the smoking alter coefficient, and then it's breaking it down by the 3 different periods that we're interested in. So the beginning of the study, the coefficient is positive. So folks are more likely to receive friendship nominations if they smoke. But then we can see that as we get to the final period of the study, the coefficient is expected to be negative, indicating that this relationship totally reverses. So now smokers are actually getting fewer friendship than their non-smokers. So again, we can use the CNN time test function to test whether or not we are estimating a better fitting model now that we're including those time heterogeneous versions of the smoking alter parameter. So again, to do this, we'll just put in our results into the CNN time test function. And use summary to pull out some information here. And now we'll see that for the joint significance test of time heterogeneity, we're getting a p-value that is slightly larger than 0.05. So this indicates that what's happening in our data is not, so the way we're modeling things now, there isn't any time heterogeneity that we're missing. We're accounting for all the time heterogeneity well enough. But again, obviously, right, this p-value is pretty close to 0.05. So it looks like there still might be some time heterogeneity in there. And for the purpose of this example, I'm going to further explore that some. So if we scroll down to the individual significance tests, you can see in particular that these indicators for the transitive triplets, we're seeing that in those later waves, again, this final wave and that between those last two waves, there is a significant difference between what was happening at the initial wave. So as a result, let's go ahead and try estimating another model where we introduce versions of the transitive triplet parameter that allow us to account for time heterogeneity. So to do this, I'm going to, again, make a new effects object. Here, just I want to note again that I'm continuing to include the time heterogeneous effects for the smoking alter, but I'm going to include additional time heterogeneous effects because you are able to do that. So you can have multiple effects that are time heterogeneous at the same time in one SOM. Here I'm using the include time dummy function again, but doing this for the transitive triplet parameter, which I'm specifying on the second line. Here you don't need that interaction argument since the transitive triplet parameter is an endogenous factor, so it's not relating to any actor level variables. And then again, time dummy setting that argument equal to all. Now we can see in our effects object that the transitive triplet time dummy column is set to all, so that indicates that transitive triplets will be modeled as a time heterogeneous effect. So let's create a new algorithm, and then we can use the CNN07 function to estimate what's going on here. Right, just from looking at this, you can already see now we have more parameters in our data because we're including more interactions to test for time heterogeneous processes. Let's check out the results. And now I'll make this a little bigger. Now you can see that in addition to interactions between smoking alter and the time dummies, now we also have interactions between transitive triplets and the time dummies as well. We also have the time dummies. Again, there are only two of them. We didn't have to create more time dummies. It's just these two additional interactions that we got by incorporating the time heterogeneous version of transitive triplets. If we look at these in a little bit more detail, you can see that the baseline transitive triplet coefficient is positive and significant, as indicated by the very small standard error. So, right, this is giving evidence for transitivity, not surprising given what we know about social networks. However, if we look at these transitive triplet coefficients, we can see that at later waves of the study, we're seeing actually a slight decline in transitivity. And in fact, during the final period, it looks like that is a significant decline that we are seeing given the small standard error. So what that indicates is that as time progresses, we're actually seeing a slightly less intense tendency towards transitivity in this data. This is probably a little different than what we'd expect theoretically, and as a result would probably require some further exploration for us as researchers to kind of unpack what's going on there. I also have code here too, how we can plot the results as a bar graph in ggplot. And here, this is the expected transitive triplet coefficient across all of the different periods. We can see that unlike the smoking alter coefficient, the changes here are not as stark. Instead, right in period 3, even though there's significantly less transitivity, still a really large and positive coefficient during those time periods. Finally, we're going to just use the Sienna time test function again to see whether or not the results, whether or not our model is doing a good job accounting for any time heterogeneity in across these different processes. So now we can see the p-value is quite large, 0.23. So this suggests that our model is doing a good job accounting for time heterogeneity. All right, as a final note too, I just want to mention that it's possible to interact in effective interest for just some of the time dummies, but not others. So what this does is it'll change your reference category and alter the way that you interpret your coefficients a bit. But this technique can be really useful if you want to improve the fit of your SAOM, especially if you have like one time period that's a lot different from the other time periods in your sample. So for example, if we go back to the smoking alter effect in period 3, things are really different than they were in periods 1 and 2. So what I'm going to do is show you all how we could only include an interaction between the time dummy for period 3 and the smoking alter coefficient. So first, let's create a new effects object. Here we're going to use just our original effects. So if we look at that, you can see here the time dummy column is in here. All of these effects are time homogeneous. But we're going to use the include time dummy effect to now include some time heterogeneous effects. Again, we're going to do it for the smoking alter SAOM effect. And then by using time dummy, the time dummy argument, this is where we're going to change things up a bit. Here, instead of saying all in quotes, we're just saying 3 in quotes. So what that means is that we are only going to include a interaction between the time dummy and the smoking alter effect for that third time dummy. So we're not going to include one for 2, instead only for that third time period. It's also possible to put multiple periods using this command. So right, I could do, if I wanted to look at 2 and 3 together, I could do that. And I would just need to put a comma between the different periods that I'm interested in. But we're just going to look at period 3. Now, if you check out your effects objects, you'll see that in that time dummy column, it has appeared. But instead of saying all, now it just says 3. So that means that we're only going to include an interaction between the third period time dummy and smoking alter. All right, let's go ahead and estimate that SAOM to see what that looks like. All right, and now that that's finished, we can check out the results. As you can see here, now, right, we only have one time dummy, and we only have one interaction. And this dummy 3 indicates that it's for the third period. So what this is telling us is that there is a significant difference in the association between smoking and receiving friendship nominations in the third period as compared to the period 1 and period 2 pulled together. So right, because our reference category is now 2 periods at the same time, I don't recommend doing this if you are interested in substantively interpreting what these interactions mean. However, by including just a single interaction like I did here, this can be useful if you're trying to improve the fit of your models. This can help with convergence if again you have a scenario where one wave just looks really different from, or one period looks really different from all of the other periods. All right, so that is all that I have for you all. Thanks so much for your attention and time. I really look forward to meeting you all and hearing your questions in the Q&A. Bye, everyone.